Hello there. Welcome back to Project 1, Section 2, which is 16-bit variant chips. In this chapter, in this section of the project, we'll be building the following chips using the elementary gates that we built in the previous video. So what are the chips that we are building today? Not16, And16, Or16, and Mux16. These are the 16-bit variants of the elementary chips that we have built so far. Let's get started with the first chip, which is the Not16. What is Not16? The logic is still the same as NOT gate. If the input is 0, the output is 1. If the input is 1, the output is 0. Now, the input, however, unlike the basic NOT chip that we built before, has 16 bits or 16 digits to it. And these are represented by indexing. You have input of 0, input of 1, input of 2. The numbering or the indexing in computer starts from 0. And since we have 16 digits, the indexing starts from 0 and ends at 15. So we take the first bit, which is the input of 0, pass it through a NOT chip that we have built before to get the output of 0. Similarly, we pass input of 1 to the NOT chip to get output of 1. And by extension of this process, we'll be passing each value through the NOT chip and getting output. So this will be the entire Not16 chip. So you see that input has 16 bits, the output has 16 bits, and you see that you're using 16 NOT chips, or the NOT operation is being performed 16 times. And this 16 is how you get the Not16 name for your chip. And this will be the representation. And you see this line and the number 16 saying that input is of 16 bits. In computers, this is called a 16-bit bus, which means that when you implement it physically, there'll be 16 wires going representing each bit, and the output is also 16-bit. And this is your NOT gate. We'll look at the HDL implementation in some time. Now let's move on to the next chip, which is And16. Okay, let's take an example here. I've taken a 16-bit value. You can see the values are 1001, 1101, so on. So what is the output? Wherever there is 1, you write 0. Wherever there is 0, you write 1. Pass it through the Not16 to get this output. You get 0100, 0010, 000, 4 zeros and 1101. 1 is being replaced by 0 and 0 is being replaced by 1. Let's move on to the next chip, which is And16. We need two inputs for AND gate. Let's consider A and B. A is of 16 bits and B is of 16 bits. And their addressing will look as this. Similar to the NOT chip, you'll have A of 0 all the way to A of 15 and B of 0 all the way to B of 15. Now, how do you perform AND operation? You take A of 0, you take B of 0 and pass it through one AND gate that we have already built in the elementary chip to get the output of 0. Similarly, you do that for A1, B1 to get out 1 and so on to get all the way up to out 15. And you see again that output is of 16 bits and hence the name AND of 16. This will be the symbol that we use to represent a 16-bit AND chip. You see that A and B both are 16-bit buses and the output is also a 16-bit value. Let's take an example. So what does the output look like? You take one bit from A, one bit from B, compare them. If both are 1, the output bit will be 1. If either one of the elements or one of the bits is 0, the output is simply 0. Let me take the first 4 bits of A and first 4 bits of B. You see the most significant bits, the values are matching. So you get 1, 0, 0, 0. And continuing that logic, you should get this output. You can take down a piece of paper and verify this. You should get the following output. Now moving on to the next chip, which is Or16, which is very similar to the And16. Take 2 bits and push them to an OR chip that we have built in the elementary gate, and you'll get the corresponding output bit. And the output again is of 16 bits. This would be the representation, symbolic representation for Or16. You have a simple OR chip. A and B both are 16-bit buses, and output is also a 16-bit bus. Now I'll take the same example as I did with AND gate, and I'll just answer for the first 4 bits. 1 and 1 will give you 1, 0 and 1 will give you 1, 0, 1, 1, and 1, 0 will give you 1. So take 2 bits, compare them. If both of them are 0, return 0. If at least one of them is 1, the output will be 1. You can verify this on your own. Let's move on to the last chip of this section, which is the Mux16. So same logic, take 2 bits, pass it through the Mux chip, and the difference is you'll be using the same selector signal or the selector bit for all the Mux chips. For all these 16 bits, you'll have only one bit, the selector signal. So output is still 16 bits. And this would be the representation. You have a Mux chip, A, B, and out are all 16-bit buses, and selector is a 1-bit bus. Let's take an example. So I've taken the same A and B values from before. If the selector is 0, then the output is A. We select A and the entire 16 bits of A, which is simply A value. Whatever input you have given A, will simply get output. And if the selector signal happens to be 1, it will be this. So that was the end of the 16-bit variant chips. Now let's get moving ahead with the implementation part. And you might ask, what is the importance of Mux16? In the next project, we'll be building an ALU, which is an arithmetic logic unit. So you'll see that Mux is of great importance there. Okay. All right, let's get going ahead with the implementation now. All right, we're back to the implementation, HDL implementation. The first chip is Not16. You have an input array of 16 size and output array of 16 size, or you can call it a 16-bit bus. So it's just not 16 times. We'll just go ahead with that. Not the first input is input of 0. The second, the output corresponding is output of 0. I'll just copy this. Let us be a little lazy. All right, so the next bit would be 1. It's just change in addressing. The logic, everything else is the same. Just push it here. So first 8 bits done. We'll just go ahead and change it. Yeah. So the indexing starts from 0 and ends at 15. Just 8. I think I can use something different. Let me do this. Let's do 12, 13. 14 and 15. So there you go. Starting from, we are implementing 16 times the not chip, one chip for each bit, and there you go, you have from 0 all the way through 15. So now let's just run this. And there you have it. The simulation was successful. Let's move on to the next chip, which is the AND. I'll do a little bit of a lazy work here. I'll just copy this, so it'll be useful here. So under the parts, I replace whatever I've copied. The thing is, not the signature is different. It takes one input and returns one output. And however, will take A and B as input and return output. So first let me change all the not to and. Yes. And then let me change all the inputs to okay. I'll just write A is A off, comma, B is B off. All right. So let me just do 0, 1, 2, 3, 6, 7, 8, and 9. And there you have it. We are performing AND operation 16 times, once for each bit. So you take 0th bit of A, 0th bit of B, and return 0th bit of output. And so on for all the way up to 15 or the 16th bit. And that's AND 16. Let's go ahead and run this. It says HDL code, no syntax errors. Let's see if the simulation is successful. Yes, it is indeed successful. I'll be a little bit lazier. I'll just copy paste this to Or16. Yep. So just changing the and to or should do the job for us. Same. Take the 0th bit of A, 0th bit of B, perform OR operation, store the value in output of 0. Perform that operation for all the bits. And the addressing goes from 0 through 15. Run the code now. Yes, there you have it. That was Or16. Let's move on to the Mux16. Same operation, same, everything is same. And yes, but and Mux have their differences in the signature, because Mux takes A, B, and selector signal as input, but OR takes A, B only, so we'll have to add selector also. Let me just go ahead and replace this with so what I've done, I've just added selector signal. Selector, as we have discussed previously, it will stay universal to all the chips, all the Mux gates. So you have a 16-bit bus for A, 16-bit bus for B, but only 1 bit for selector. So selector goes through all of it. Yeah, that looks good. The HDL has no errors. Let's run this. Yes, the simulation was successful. and we've successfully completed all of the 16-bit variants, both the theory and the implementation in HDL. In the upcoming video, we'll discuss the following chips, which are the multi-way variants. You have the OR 8-way, Mux 4-way, Mux 8-way, DMux 4-way and 8 ways. This was quite a short video. In the next one, it'll be a little bit longer. And that will conclude project number 1. In project number 2, we'll be doing adder chips and ALU. So things will start getting interesting from now onwards. So stay tuned for the next video. Thank you.